So, so hello everybody. Thanks for coming again. So I will start with an explanation that I gave yesterday with the hands. It was not necessarily easy to follow, and it is much easier with a whiteboard. Yeah. So it was just to explain a very simple an idea which is very powerful, though very simple, which is having the pattern matching in mind. Okay, so we provided two inductive types, one for colored points with only one constructor called CP with three components. The first component was a color, which could be itself either a new color like yellow or an old color, a traffic color with a hat called TLC, or another color called gray with a natural number. And the other components of a color point are the coordinates. I call them here XY, X1, Y1, etc. Or I could use the same. Okay, so this is the how the type was defined. And for instance, here is a possible value, a concrete value. So CP with, for instance, I choose the second variant here. So TLC with the orange traffic light color, and X is 2 and Y is 7. Okay, so this is easy to have this in mind. And what is pattern matching? So first, you have to write your pattern. So again, a pattern is like a value, a concrete value, except that at some point I can put a name, a variable name instead of a constant. For instance, here I have a x1 instead of a 2. Okay. Here I have a TC instead of, say, green, orange, or red, and so on. Here I have an N instead of some number. Okay. So what is pattern matching? It is exactly recognizing which of these patterns corresponds to an actual value. And the idea is very simple. You just check that you have the same constructors. For instance, at the root here, I have CP in CP. So until this point, this pattern could correspond. Now I look lower and I see that here I should have the constructor yellow. Does it correspond to TLC? No, it is another one. These ones could correspond. Here I could agree. I could take this one is this one, but okay. But anyway, this pattern does not correspond to this value. Now I can go to this one or to this one. I take this one again. So does it correspond? CP, okay, but gray, no. Gray does not correspond to TLC. So no way. So, and you see that the second pattern works perfectly well. So now when we have pattern matching, you have two things. Recognizing, first thing, so I see that this one is okay. Second thing, matching, that is, making the correspondence between the variable names of the pattern and the actual values inside the actual value on the right. Okay, for instance, here I could see that, okay, so TLC, so this corresponds, and now, okay, so nothing new, but I could say that this TC has a value orange, this X takes the value 2, and this Y takes the value 7. It's that simple, okay? There is something wrong, not wrong, but I mean too specific in the example I give here. It is that you see that the patterns are very close to what I have here. But I could have another pattern which is different. So I will take another one here. For instance, I could say CP of C, say A and B. Does this pattern agree with this one? What do you think? So we will have to see, the root, okay, the root agree, okay. Then here I have TLC of orange, and here I have, okay, I put here a small letter to be, okay, this is a little c, that is not a constructor, okay. So it agrees because this is a variable, okay. So in that case, C will catch all these things, TLC of orange. Okay, so this is something a little bit more general. So the variable is not necessarily a single value at the end. It could be a full subtree. Okay, this is what we see here. And A and B are like before. E will be the 2 and B the 7. I will not write because the whiteboard will be too complicated. Okay, that's all. Okay, so the thing to understand again is that with this mechanism, with computing mechanism, we have something very powerful. Okay, and it is one of the main features of typed functional programming. Okay, and okay, so I will erase this. I show another example which still has not been introduced, but if you did the exercises or if you have some experience with OCaml, for instance, we will recognize what I am saying. But anyway, it is not difficult at all. Here I considered a tree-like structure which is very shallow, only 3 levels. Okay, so this is not okay. We see the ID, but we can make this ID working on deeper trees, tree-like structures. For example, consider binary trees, okay, which are made of only 2 nodes, 2 kind of nodes, a leaf and a node with a left subtree and a right subtree. Okay, so this is what I expect. Okay, and leaf maybe will be colored by, okay, maybe let us take colored trees. So at the leaf, I have a color, a traffic light color, say. So what could be an actual value? It could be something like node of, yeah, node of, and I will stop here. Okay, leaves and something at the end of the leaf, for instance, red, green, and so on. Okay, whatever color of the type orange or whatever. Okay. Now consider a typical pattern matching, a program based on pattern matching on such trees. Basically, okay, I could have deep patterns, or I can have also very simple patterns. Usually, we will only use simple patterns, but not always. So the typical pattern will be given here. So the first pattern is L of some color. The second pattern is node of left subtree and right subtree. Okay, so a typical program on binary trees will proceed by case. I have a choice between these 2 shapes, possible shapes, and I will see and have to compare these 2 patterns with the actual value which is input in my program. Okay, so in that case, does this pattern agree with this actual value? No, okay, because the roots are different. This one, okay, because the root agree. And then L will catch all this subtree, is L, okay, and R will catch all these subtrees. Okay. And now, if you know a little bit about recursive programming, so something very intuitive on for computer scientists, for programmers, you will see that you can make computations on any value having this shape just by repeating this pattern matching. At each stage, you ask whether you are in this pattern or in that pattern. For instance, suppose that you want to compute, say, the size of the tree. So the size of the tree, there are several ways to define it. Say, for instance, the number of leaves, okay? Suppose we want to compute the number of leaves of the tree, okay? You will say that if my tree has this shape, I have one leaf. If my tree has this shape, the size will be just the sum of the size of this one and of the size of this one. Something I think you used to write, and you understand how it works because you understand that it works because in order to okay, there are no colors. Okay, so okay, no problem. So I will write another way. Why does it work? Why could I compute the size of this tree, for instance? So I will just put a star at the point where the computation is performed. So I say that, okay, this one, okay, so I will see that the size, okay, how to say it returns, I write this one, and here it returns the sum. And don't write too much, it is enough. So the point is that here, oh, I don't know, I have to compute something about that, something about that. Let us see later. I put this on my stack of things to remaining to be done. Okay, I will have an addition to make. Okay, but anyway, what I see is that when I am at this point, I know the answer for this subtree. Okay, I know the answer. I know that it is 1. Okay, it is 1, but I just put a star to say, okay, here I know the answer. Here the same. I know the answer. Okay, and put here say the same here and here and here. So I know the answer at the bottom of my tree. Okay, and then for instance consider this one. Okay, I know the answer here, but if I know the answer here and here, I can compute the answer here. Okay, just make the sum. Okay, so this one is start again. Okay, star. Okay, so I have the answer here. Not finished. Here I don't have the answer. But anyway, star, I make my star here and finished. So you see that I have the answer here and here. So thanks to this rule, I can finish my computation. Okay, so you see that how it works. So basically, functional programming on data represented by trees like this. It is just repeating recursively a pattern matching and provide the answer. Okay, that's all. So in functional programming, you have two things to remember, two very important things to remember. One, we saw yesterday at the beginning, functions can be input and output of functions. Okay, we discussed that on that for 1 hour maybe. And the second thing, which is more specific to typed functional programming, everything every data at least can be seen as a tree. And we have as computer scientists, okay, so I add something. You are programmers and you know how to represent in the memory tree-like structures. You know that they are made of pointers and this kind of things. Okay, so you know that trees exist in some sense, trees, this and this kind of thing. You know that they exist. You have an advantage over ordinary mathematicians. Because for mathematicians, they don't have this notion of memory, pointers, and so on. So they are not used to that. And when mathematicians want to talk about trees, it's complicated for them. They have to represent them by using set theoretical construct, and it makes things rather a little bit too much complicated. For us computer scientists, it's much more simple. You just make this drawing. We know what you are talking about, and you know that, okay, after these are some details about implementation, but we know that this can be managed. We know that. An additional point I want to add here, it is not written in my notes, it is that, yes, okay, you know that we have this mechanism made of pointers. You know that actually you have to make something like memory allocation and so on when you enter into the details. Management of memory allocation and so on is completely automatic. So, okay, I don't have the time to explain why, but this is something very important. The programmer is not annoyed by these small details. Okay, this is a big difference with programming in the C language, for instance. You have always to think, okay, I have to allocate, I have to deallocate. Oh, but if they allocate and somebody else has an alias on this part of the memory, it would crush my program. So this is a very well-known source of bugs in imperative programs. So in functional programming, we have the ability to talk about growing structures like trees, you see, without being bored by the details of memory allocation and also deallocation, okay, freeing the memory. So we don't have to worry about that. Think it is very efficient, okay? So once you have this in mind, okay, we have the power of, so we can just make our drawings and it works exactly according your intuition. And I really want to rely on this kind of primitive intuition that we have. So, you know, if you open a book on algorithmics, etc., people make drawings saying, okay, I represent this graph, this tree, and so on, just with drawing, and we understand what it talks about. And that this is what I want to do. And the point is that using pattern matching, okay, it makes this kind of drawings a little bit more formal and clear, but it works exactly as you want.
By the way, you say that functional programs don't have to worry about the allocation of memories. And then, yes. So for these kind of structures, how they are stored in memory?
They are stored exactly as they would be stored if you write a C program. So, okay. So the very point, okay, if you want to see about that, is you have to ask when memory allocation is performed,
yeah,
and when memory freeing is performed. Okay, so memory allocation is performed when when a constructor is evaluated. So when you say, for example, OCaml, let something equal, I don't know, for instance, n of the thing I wrote here. Okay, here you allocate the memory, or in Coq, definition equal this. Okay, here you allocate the memory. Now, if you say definition new tree, but it is not the new copy, same tree equal this tree. Okay, so let us write. Okay, so I can. If you write, okay, I write it in Coq, definition, okay, tree 1 equal this one with the Coq syntax, okay, and of the parentheses and so on, okay. Then if you write definition 3.2, 3.1, then there is no memory allocation. It is just sharing the pointer.
Okay. So
Okay.
Okay.
If I don't write 3.1, but I rewrite all this,
Yeah.
it is a new allocation.
Okay.
If you ask if they are equal, mathematically equal, they will be equal. So the system is able to, for the equality, will just perform the recursive traversal of the two trees. So if you write this one, okay, they are equal by this pointer equality in some sense. Okay. So the same in OCaml.
Yeah.
Okay.
So this is allocation.
This is allocation.
And then freezing.
So free memory, you don't have to care about this, but so the memory management system of the how to say the running the interpreter, for instance, or the compiler, what he does from time he keeps there are different mechanisms. One of them is to keep a track of what actually is alive from the root, in some sense, of the system. So from time to time, the memory system will look, okay, does this exist? This one has no path from the root to this point, it could be removed. So actually, there are two systems which work together, one which is quite frequent and not complete in some sense. Okay, I don't remember the name exactly. And so this is okay. So this is called garbage collection. This is the very name to know. So this garbage collection, okay, works. So you have two mechanisms, at least in OCaml. In Coq, I don't know. In OCaml, there are two mechanisms. One which is quite efficient runs from time. Because many structures are created and freed very quickly, okay, but others are more difficult to track. So from time to time there is a more heavy mechanism which will, and you can okay, if you are interested in this kind of thing because you have performance issues, then you have to look in the documentation to see how to tune these mechanisms. By the way, garbage collection was considered as a drawback of functional programs for a long time. It exists since the very early days of functional programming, from the 60s, Lisp. Okay, and it became popular because of Java. So, which is not at all a functional programming language, but Java was the first mainstream language with a powerful garbage collection mechanism, and by the way, which is much less efficient than the one of OCaml. Okay, because you have to garbage collect objects, and objects are very big things, complicated things. Here, the garbage collections is about on very simple things, so it's more efficient by design. So, other questions? Okay. So maybe
yesterday they were
yes. So I don't remember the questions. Yes, maybe yes. Okay. When it was about lazy, and I don't remember the detail. And the other about the other was about invariant. I said variables are invariable, and so I could be misunderstood at that point. So okay, so I can explain also here is something to be caught.
Yes, I know. The question that a variable is invariable within a section.
Yeah. So in both in Coq or in functional program, we have a scoping mechanism. It is the point is about scoping. So in Coq, it is section section and end section, okay, or within the body of a function. Okay, I introduce a new variable, or a pattern matching also. Pattern matching, each pattern, each time we succeed, we open a new scope with the variables that catch the subtrees. Okay, so we have several opportunities for scopes. So I will just write in the C-like way a scope, whatever it is. So if I am in the C language, okay, I could, I think the syntax something like this. I could declare some variables, call it x, okay, and then use x several times in my scope, okay. What I mean is that in an imperative setting, the meaning of x, I mean okay, in that case, it is the contents of the memory cell referred to by x changes. You cannot claim that this x has the main value than this one, as this one. It is probably false, very probably, okay, because you have many assignments and many side effects. Whereas in functional programming, so you don't say that, but you say, okay, in Coq, you would say something like a variable x, for instance, with a type, okay? Then you refer to x in your section several times, or in the body of your section, of the same. All values which are that x refer to are meant to be the same value. And you can understand this when you are in the case of functions, for instance. But that's the same for pattern matching, by the way. Okay. When you say an x, okay, it's like this, and then, okay, an expression with x several times, okay? So, sorry, I need more room here. So if you take this function, I put a big parenthesis around it, okay? And I apply it to some value, say 5. Then you see that x will be substituted by 5, and the function will be evaluated, and everywhere x is equal to 5. It's the same. So this is what I mean by x is invariable. Does not vary. It is the same everywhere within its scope. Okay, so here it is applied. We see that it makes sense, but even here we still don't know the value. It is an unknown value at this stage. But it is always the same value. Okay, but not the case for imperative programming. So this is the big difference between functional programming, pure functional programming, and okay. So by the way, one of the things I wrote somewhere, Coq is a really pure functional language. OCaml is not a pure functional programming language. But you can for what I will make, everything can be everything which is translated from Coq to OCaml will be, of course, a pure functional program. So what I mean by pure means without side effects. Okay, so we are comfortable with that. In OCaml, it's possible, or variants of ML, it's possible to have a kind of side effect, but there are you cannot write like this. You need to say things like okay, so this is in OCaml. You have a syntactic symbol, an exclamation mark, to say, okay, this is not a pure value, so be careful. So in practice, in everyday life, we, as far as possible, don't use the side effects, but from time to time, we need them for instance, for read, write on the keyboard or in the memory, etc. These kind of things. So we have a kind of balance between imperative and limited imperative as far as possible and comfortable pure functional programming. We have this feature. So in the Haskell language, it's a little bit different. Haskell is much more pure in some sense, but then we still have to deal with the real life, with read and write. So they have a mechanism called monad to talk about that. And the very point of this famous monad is to, in some sense, take into account the evaluation order. So yes, this is a very important point. In functional programming, you write functions. You know, I illustrated that before. I was able to put my stars in an arbitrary order. At the end, the result will be the same. So this is one of the important of functional programming. Basically, the result does not depend on the evaluation order. Okay. While in imperative programming, okay, we have to be aware we do that, then that, then that, and the result will not be the same if we start. Okay, you see. So as OCaml is a little bit imperative, you have to be aware in this part of the evaluation of the order of evaluation. Okay. So there is some. So OCaml actually says quite precisely what we can say in OCaml very precisely. We can control the evaluation order when we want to do that. If we just write fun, apply to fun, this kind of thing, there is an order, but we are not supposed to know it. So right to left, but okay, I don't tell you. Okay, but if you use the other mechanism, if you know it, which is let in, then you control completely the evaluation order. And Haskell does not have that. So, but you can simulate this and let in using monads. Okay, so this is okay. So let us go back to the coq. So now I will try to share the screen again. Is it okay on the screens? Yeah, of course. But already at least you have the screen. So what I would like to do is to show you a number of how could it could I okay. I would try to show you advanced features, amazing features, using only basic notions. Okay. Alors, let us tell me when it is big enough. Bigger?
Okay, this is fine.
That's okay. So yesterday we went. Where did we go? Okay, homework. I think this one has no special interest. This one is interesting, but I will go back to this one anyway. Did I show you this one? I don't remember.
No.
No? Okay, so okay, so let us go very quickly here. So remember, I state a theorem. Okay, so I have to make this bigger. Okay. Yes, I think I showed you this one. Here. Proof. Okay. So I want to prove something for any. Ah, no, I didn't show you. I'm not sure. So anyway, okay, something which comes from proof theory, how to prove a universal statement. Okay, so the idea, you know, is that, okay, let us take an arbitrary TL color and show the right-hand side for this arbitrary color. So let us okay, let us consider an unknown but arbitrary C0. It is performed using this intro tactic. Okay, so one of the basic. Okay, I am not. Okay, okay, and now I am back to the previous what I could see with the section mechanism. That is, okay, I have in my current world some TL color called the C0, and I have to show that C0 is equal to C0. Okay, and you know how to prove this just by invoking reflexivity. Okay, so the next point is that intro can also be used to prove an implication. We will see very soon why this is the same keyword. It is not by chance. Okay, so let us prove that. C'est un peu embêtant ce truc. Okay, let us prove that for all C, if C is equal to red, then the next call of C is equal to green. Okay. So again, so same thing as before. I want to prove something which is universally quantified. So let us introduce it with some names here. I choose C0. I could choose A or whatever. Okay. Now I need to prove this implication. I could say actually I could pronounce it the same. Let us take any proof, an arbitrary proof of C0 is equal to red. But I say this, okay, I assume that C0 is equal to red. Okay, so let us assume it. So this is a comment. Okay, so again, I will say, let us introduce this name, C0 is red. Let us introduce it. And this is just an unknown proof of the equality. Okay, so now I have two things in my environment, C0 and C0 is red. Okay. Now how could I use what I have in my pocket here? But you know that I want to use this equality, and remember, in order to use an equality, the keyword is rewrite. Okay, well, there are some revariants, but basically it is rewrite. Okay, so I will rewrite this equation saying, I will say rewrite this name here, because this is the name of the justification that I have the equality. Okay, so I say rewrite here, rewrite of the hypothesis. Let us rewrite it. So at the place of C0, I will see a red now. Okay, I see my red, and now okay, now I can compute. Now before I could not compute because I had a variable, nothing to. Now I have a red. This can be computed. So I say it by CBN, and I add, because I am very accurate here, I see CBN of next call. Okay, so the left-hand side reduces to green, and now clearly I have green equal green. It can be proved by reflexivity. So just some okay, some little tricks to write the same things faster. So I take the same theorem, same statement, okay, and instead of saying intro C0, then intro this thing, so instead of using two intros one by one, I will make the intros in the, okay, like this, using the, well, be aware of the S here, it's the plural. I introduce several things at the same time. So, okay, so I have directly my environment, and as before, I rewrite, I compute reflexivity. Okay, so you can see the same thing using using a section. So I open a section, I have a variable, and I could state the theorem like this. If C0 is equal to red, then if C0 is equal to red here, then okay. So you see a small difference is that here the name is C instead of C0, but okay, the name does not make a difference. Okay, so okay, I guess that you are able to do that. Just intro, CBN, and reflexivity. Okay. So if you are stuck in this kind of thing, so now we have this one. Maybe we can try to do it together. So I want to prove. So I left my section. Yes, okay. So I have a quantification here for all C. Then next call of C returns is equal to C. Okay. So what should I do first? Intro. Okay. So I introduce my C. Okay, I can call it C2. Okay, I change my mind. Okay, so I have to prove next order of C2 is equal to C2. And what could I do here? Okay, I can try to compute. Boy, I'm lazy. I just write CBN, and nothing happened. Nothing happened. Why? Because here it's always the same. Next call of C, it is a variable. Nothing. I don't have enough information to progress. Okay, and the same for this one. For instance, next call of a result on which we have no information. So we have 3 function calls, but no one of them is able to induct. It could work, but it's too complicated for me. Okay, but you are almost at the what? I actually need to reason on the possible values of C. This is okay. This is something which that induct is also able to do, but we have to think more accurately. It's better to think a little bit more accurately. So what I want to say is that I need to explore the different possible choices for C2. If I know a little bit more on C2, then I will be able to compute. Okay. And now, what are the choices possible? Sorry. What are the possible choices for C2? Green, orange, and red. 3 choices. And so, okay, so this is very basic. It will be destruct. Okay. Reasoning on the 3 possible cases. Destruct. Reasoning by case, destruct. Remember, reasoning by case, destruct. Remember, okay. So let us destruct. C, and I know that there are 3 cases. Sorry. So as I am, I like to make things explicit. So if I have time, I would even say in comments within between the bars, what are the constructor expected? Green, orange, yellow, but here I just put without comment the 3 choices. Okay, and I see C2. It is called C2. Okay. Okay, so we see the 3 possible choices. Okay, and now I can compute. Now I can compute. Okay. So basically something like this. So I put a bullet for the same one. Let us compute both. Just CBN because I don't have too much time. Okay, green is equal to green. Reflexivity. And the same in all other cases. I think I can try something faster. I could say I think all CBN. Because I see that okay, maybe you don't see too much here, but if I try to make the goal, oh, please. Okay, here you see the three goals. They are you see that just by reducing, I will get the result. Okay, so I'd say that for all sub goals, I want to perform a CBN. Yes, and then I can see that for all sub goals, I can say reflexivity. So all reflexivity. Okay, this is a possible way to. Okay, when you have. Well, in that case, it's easy. Okay. So now I don't forget to replace my admitted by a QED. Okay. Now my example on binary trees. So exactly what I wrote on the table on the black on the white board. Okay, so I have the type, the recursive type of the recursive inductive type of binary trees. Okay, and so I would say there is nothing new. There is nothing new because the only new things basically is pattern matching, but now you know it. And the other thing is recursivity, and you also know what is recursivity. So basically, for you, it should be easy. Okay. So for instance, here I defined what is, okay, no, it's not the size here. I define what is reversing a binary tree. Okay. So the keyword is called fixed point. Okay, so so I have something here, some explanation on the reason for this syntax. The reason is that when I write a recursive program, I need to refer to the name of this program because here I need to talk about the function. Okay, so this function, so even if for just to say that the notion of an anonymous fixed point is a little bit strange. So okay, so I will use this syntax, which is clear, I think. Okay, anyway, which is the usual the standard syntax. So I define a fixed point called with now the name of the function, reverse of a tree. We have one parameter, only one. So here, okay. But usually when you have several parameters, at least you should have at least one of them which is explicit here. Why? Because as it is a recursive function, I have one thing to ensure. Okay, I know. Okay, the thing I have to ensure is that all recursive calls are performed on a subcomponent of the input. Okay, so here my input is T, and immediately we write a pattern matching. So we will see what T is. So here, this is the very behavior of pattern matching. Pattern matching provides you the possible subcomponents of your input, of T in that case. Okay, whatever is T. Okay, so T could be a leaf with a C, a color, or it could be a node with subtrees. Okay, and what we see, so this one is there is no recursivity here. So okay, nothing special to say. But here I have J and D. Oh, okay, okay. So because it's I will change it to left and right because this was in French in the past. Okay. Okay, well, let's write it in English. Left and right. It doesn't matter, of course, they're just names. That may be easier to understand. Okay. You see that here I perform I look for the result of relativity of L, and L, as L is a subtree, I have exactly what I explained on the whiteboard. I will be able to compute it because it is smaller. It's the same things for R. It is what we call structurally smaller. It is a subtree of the also. So by the very definition of recursivity on trees, I will be able to compute the result. So in that case, I compute this one, I compute that one, and I put an n on top of them. So of course, what did I? No, okay. Yes, it is a R if I want to make. Otherwise, it's just a copy. By the way, it would be a copy with memory allocation. Okay. In that case, of course, So you see, each time here I invoke a constructor, I have a memory allocation. Just the question before. Okay, so this is now reverse. So not difficult to explain. And by the way, I just tell you that the syntax for fixed point here with the name of the function and an argument, okay, this syntax can also be used for functions. So what you did before was to say definition of this is a function of C, a row, etc. You remember? So it is important to understand that the thing which is defined is this. Okay. This is the thing which is defined. Okay, and it is a function of C. Here we define ref t again. We define ref t. It is the function of t, but as it is a recursive function, I have to say, okay, but it is a function of t, and I pay special attention on t. T will be replaced in the recursive call by a subtree of t, and okay, this is checked by Coq. That the recursive call are on subtrees because I have a pattern matching before. Okay. Okay, so this is an alternative possible way of writing things. And now I think we are at the end of the file. So prove that reversing twice a tree returns the same tree. So how does it work? So we have a for all. So let us introduce, here I keep the name T, okay, for all T. And then, as before, I would like to say, what are the possibility options for T? One is leaf, one is node. So at first I tried just the destruct, reasoning by case. Okay, so I reason by case. Destruct T as either a leaf. Okay, I will put this here. Either a leaf. So okay. So here you see that the destruct provides. Did I show that before? So when you have a destruct, okay, it is a little bit like pattern matching, but we don't provide the name of the constructor, but we need to provide, it is better to provide the names of the components, okay? So T has two constructors. For the first one, we say that it is a leaf of a C, and for the second one, we will say, the second possibility, we will say it is an N of T1 and T2, okay? So the two possibilities for okay, so I get two subgoals, one for LC and one for N-T1, T2. You can recognize the two shapes I gave. Okay, so now let us go on. First case, sorry, I have to go here. First case, I compute on ref T, and you see that according to the already, okay, maybe we should look at the definition, but okay, sorry, I will put this on the top like this. Okay, we see all. Okay, so you see that the rev of LC is LC. So, and again, the rev of LC will be LC. So if I compute, I will get here LC. Okay, I will get by computation, I will get LC. Let us check that. Okay, so reflexivity. Now, the second case, again, I can compute. I have a ref T of N T1, T2. So this one, by computation, will return N of the reverse of T1 and the reverse of T2. And again, I will the left one will be computed. So what do we get? Okay, let us see. Okay, we get n of ref t1, ref t of ref t2 is equal to that. Intuitively, okay, we think, okay, but this one should be T1 and this one should be T2, but at the moment we have no way to progress. Why? This is because we didn't try what you said before. We should not make a destruct is not enough. Actually, we should again destruct. Actually, I could try. Actually, I could progress a little bit more. I could make a destruct of T1 and a destruct of T2. And in the first case, I will be able to finish. But then for the step after, I will still be stuck. Okay. So the idea is that I need to make a destruct and then a destruct and then a destruct as many times as I have n nodes n in my structure. Okay. So you see that it is basically the same thing as computing. When I compute the ref t or the size, I have to perform my pattern matching as many times as I have n. For each case, I have to compute, okay, the sum or whatever. Okay, so it works exactly the same. I have to repeat my destruct. So, okay, we will return to that later, but at the moment, let us just say that reasoning by case is not enough. We have to do something more powerful, which is called induction. Okay. So induction is just a kind of improved destruct in some way. Okay, let us retry using induction. So same theorem, same proof, same intro T, and then okay, some explanation here. So blah 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 blah. So the point is that instead of writing destruct here, I write induction. In the first case, there is nothing changed. Okay, I have a component called L with just, sorry, I have a node called L with just one component called C, but there is nothing recursive at this point. Okay, so this is as before. The next one is more interesting. I have N with its two components T1 and T2. And what I will claim here is that I am able to have the target to be proved on T1 and on T2 by induction. Okay, so let us show what it looks like. So I have, as before, this one. Okay, so it works the same. I compute, I get an equality which is obvious. Okay, let us go to the next one. And you see the difference. Now I have my two induction hypotheses here, which says that, okay, I know that by induction, the things to be proved already holds for the subtree T1 and for the subtree T2. Okay, suppose that it holds. Okay, then let us compute. Sorry, yes, I am here. So I compute. So I get this expression, and now, no, I can progress because, for instance, this thing can be replaced by T1 thanks to this hypothesis, thanks to this induction hypothesis. So I just have to say here, how do I use an equality? Rewrite? No, not in this case. It is a rewrite. Okay. Sometimes I can, in very subtle case, I can use apply when I have an equality, but it is only when the equality are really the same. But here it is not the same thing. It is, I mean the left hand side of my equality here is somewhere inside the full expression. Okay. Okay, it is a part of my expression. So I want to replace this part of my expression by the right hand side, by T1. Okay, so So, okay, so just remember when you have an equality, so you want to replace somewhere in a sub-expression, use rewrite. And this is a very basic thing for using equalities by rewrite, except in some special cases. So this H-rank T1, for instance, so the first one, I could perform the first one. Okay, so you see that now, now I have a T1 here. Okay, and we'll proceed the same way for the second one. We write H-rank T2, second hypothesis. And now, how do I finish? By reflexivity. Okay, so that's a solution of the exercise. So you can see, I ask you, imagine that you write the same program in C, so with pointers and so on, and memory equation or whatever, okay? Imagine you write a program in C, the equivalent program in C that reverse binary tree in the same idea, and ask you to prove that this program applied twice returns the same something which is equal to the input. You have a lot of work to do. It is basically a research work. Here it is just a simple exercise for beginners. This is the power of functional programming. Okay, so reasoning, okay, here the reasoning is assisted by Coq, but okay, you could also write the proof by hand on a paper. Okay, so basically reasoning on functional programs is much easier than reasoning on imperative programs. Much easier. Okay, that's all for this one. And then I have what time is it? 10. Okay. So so I will make a pause at some point, but maybe later. Are you tired or not? Okay. So I provided you yesterday another file on one. Okay, no, I ask you to finish this one and also to have a look on another file which talks about tree-like structures representing arithmetic expressions. Okay, so what we call AST, abstract syntactic trees. So basically, it's programming on binary trees like this, but a little bit more complicated because instead of only one kind of binary node, we may have two. I think I take two nodes, one for the addition and one for the multiplication, and we can reason the same way. So maybe I will left this because I think it's once you get the ID, when you catch the ID on these data structures. Okay, so there is one thing to explain, but I think you already know that. So this is one of the illustrations of these lectures is to show how Coq can be used for talking about semantics of programming languages. Okay, so for talking about semantics of programming languages, we have to explain what is the mathematical meaning of expressions and what is the mathematical meaning of programs, of including imperative programs. So we will talk about, we will take a very classical example of a simple programming language called while or imp, according to the authors. So with just assignments, so this kind of thing. So, okay, so we will see the details later. The important point is to understand that we don't reason on the text of the program, but we reason about a well-organized representation of the program. It is represented by a tree again. So you know, I hope that when you use a compiler, GCC or whatever, the first thing, or OCaml, the first thing which is performed by the compiler or the interpreter is to analyze the string, the text. It is a kind of the file, a big string, okay, to cut it into small pieces and to make something which can be worked. Okay, this thing is a tree. Okay, so we will consider that this work is is performed by somebody else. This is called parsing. Okay, so I will not talk about parsing, and the result of parsing is a tree, what we call an abstract syntactic tree, syntax tree. Okay, so it is really like this kind of thing, but instead of just an n, we will have, for instance, for arithmetic expression, we have something saying, oh, this is an addition, but it is a data structure. It is not a function call. It is just a kind of kind of color, say, which is called addition or multiplication or whatever other operator, and this can be made richer and richer. So basically, we then work on data which represents a program, a data which has the shape of a tree. Okay, so I think I will go back to this later, because once you understand this, we just understand that we just need only one thing: how to. Okay, so we will show this illustration on the semantics later. Now I would like to go further on the amazing things, on the surprising things of type theory, in order to make more interesting programs on trees. Okay, so I will go to another file, which is called not this one, Coq 01 surprise 1.v. So I stop this one. So this, okay, no. Okay, this one. So again, enough, more. Is it okay? Bigger?
Yeah.
Like this? Okay, okay, okay. So I will present advanced topic on very simple, stupid examples, always example of traffic light colors. Okay? So the thing I would like to show right now, because okay, so we have seen two things before. We have seen a little bit of functional programming, how to define functions, how to define data types, tree-like data types. Okay, and we also have seen how to state theorems and prove things on prove theorems. We have seen two different things. Okay, now I will show you that we can define a program in the same way as we prove the theorem using tactics. Let us show you. So I take the same example, colors. So you know this example, okay? And now the definition you already know, next color, okay? Nothing new until now. So I don't know why it is. Okay, okay. Okay. Now I will show you an interactive definition of this function. So usually as programmers, of course, we write a program, a full program, a big file, and we push the button compile, and we get many bugs. We get many mistakes. Okay, the compiler says you, okay, this is wrong. Okay, so here we can make something more interactive. Instead of writing this large and big definition at once, okay, I will show you how to develop it by small steps, okay, using small steps. So let us do that now. So I give the interactive definition of next call. I call it next call 2, okay, because next call is already defined. I cannot redefine it. Let us try. If I forget the 2 here, Coq will say, next call already exists. Okay, so let us call it another way, because OCaml behaves a little bit differently. OCaml will say, okay, the new definition with will hide the previous one. Okay, in Coq, it's consider that they shouldn't. Okay, because I think if you do that, it is probably a mistake. Actually, it is okay for this usage. Anyway, so we try to define this, and instead of saying colon equal, we say just dot. Okay, I just state the type of my definition. Okay, here I should say what is the expected type. Okay, I say proof. Okay, I like a proof. Okay, oh sorry, it is again too small here. Okay, so what do I? Oh, it looks like an implication. Okay, so let us say, okay, so what does it mean? I have an input, which is a TL color. Okay, so let us say, okay, let us say, I have a TL color in my pocket. I call it C, for instance, intro C. Okay, and it says, okay, so given a C, which is a TL color, I would like to provide a TL color. Of course, I could say I can return C. It's the simplest thing to do, but I don't want to return C. My intention is different. My intention is to return something which is similar to what I defined before. So I would like to say, okay, it depends actually on C. If C is green, I will return something. If C is red, I will maybe return something else. Okay, so I want to reason by case on the possible value of C. Okay, I don't just want to return an arbitrary definition, but this definition which depends on the value of C. Okay. By the way, I can type this command, which is show proof, and show proof actually shows you what Coq is doing. Coq is saying that okay, I will make a function of C, a color, and now I have returned something. I don't know what. So what you see here, it is a kind of interactive definition. If you look at this, I say, okay, when I define this, I start by saying, okay, I will make a function which returns something, but I still don't know what is the something which is after the arrow. So this I saying intro C. Okay, this is like saying, okay, it is a function of C. Now I want to reason by case on C. Okay, so reasoning by case in the functional way is performed by pattern matching when I write a program. In interactive mode, you know this command, it is destruct. So I will say, okay, I have three cases. These three cases for C, the case for green, the orange, and red. Okay, so let us destruct C. So here in comments, I say the three possible constructors, but okay, on my screen on the right here, I don't see that the first case is related to green, the second related to orange, but I know that in my head. If I want to see that, I can again say show proof, and you see that here the incomplete program that I have is exactly what I had before, except that on the right of these arrows there, I have still nothing. So you can see the shape here, fun of C, match C with green, orange, red, but on the right-hand side of each arrow, I have things to be completed. So I have three things to be completed, and these three things correspond exactly to my sub-goals here. By the way, it's goal. Okay, this one is called goal 2, but actually, okay, here the name is goal 0 with okay. But anyway, that's exactly the same. Okay, so we show our proof. Now I go on the first subcase, on the first case. So I can show proof, but nothing new here. And I will say, okay, in this one, okay, so I want to complete what is here. I will say, okay, for green, my answer is orange. This is my intention for this specific function. I want to return orange. I could choose another one, but I choose orange. So I say exact orange. Okay. So I would like to have this one on the top. Okay, so I will see. Okay. Let us go to the second sub-goal. Again, I have to give an answer for the second case. Let us say I answer red. So I can again show the proof to see what I have. Show proof. And you see that my current uncompleted function is match C with green, orange, orange, red, and red. I still have to answer this one. This is my current sub-goal. So you see, I really develop my function step by step in an interactive way. And using the show command, I can ask, okay, what is the hole in my code to be filled? Okay. So let us finish. Last bullet, exact green, defined. And if I print next call to now, what you see, it is exactly, okay, I would like to have my mouse. Yeah, okay. You see that I have exactly the code that I wrote by hand at once at the beginning. Okay. So you see that using the interactive mode that we use for proving theorems, I can also use the same commands to develop function. Okay. Same activity. And of course, this is the same code, so I can also compute. I can compute next call to apply to red. It is the same. It is really the same. Now, okay, now I will show you something which is between the two, because here you see construct expressed with fun, expressed with match, okay, while here the corresponding keywords, I would say, are a little bit different. You see that instead of fun here, I wrote intro. Instead of match, I wrote destruct. Okay. Is it possible to really do things that I claimed? That is, writing the program as written here, step by step. The answer is yes. And here is the most powerful tactic of Coq, which is called refine. This is a universal tactic which can be used everywhere. So any of the tactics I showed you before, such as intro, destruct, and many other, or apply that you mentioned, but I still did not introduce, all these tactics are special cases of refine. Even reflexivity is a kind of refine, but it is a little bit complicated. So I don't want to show you at now, but otherwise you have refine. The only real thing which is not a refine, it is computation, CBN typically. So CBN actually is nothing. Okay, so we will see that later. This is something which is very important as well. So let us play with refine, do exactly the same activity as before, but replacing intro, destruct, etc., just by one construct, refine. So let us go. Let's call 3 now. So I said before, intro C. Okay, so I will replace this intro by something else. So here I use another keyword which is undo. So undo actually, my fidelity allows me to go back one step backwards. Okay, so I go back. I forgot my intro. I return to the original statement here. Okay, which is the type, my target type here. So I go back here, and instead of saying intro, I say, okay, my function is func arrow, and I don't know at the moment. I put an underscore. So the underscore here means, okay, it is a whole to be completed later. But I say that, okay, it is func something. So refine func. So now I don't need to, okay, I could make my show proof, but I have no more information than what I wrote on the left. I see you see exactly, except that the underscore is replaced by goal like this. But okay, I have no more information. Okay, now again, let us replace the destruct. So I write my destruct. You remember the effect. So I have 3 goals like this. Let me undo this destruct and go back to yes. So what I had, yes. So I have a fun with a C in my environment. I have to provide a TL color. Now instead, so I want to reason by case on C in order to reason by or to program program the same program by case on C. Okay, I say refine match C. So you see exactly my incomplete piece of program. So I say that this hole here, sorry, here, this one, you see on my cursor. So this hole will be filled by a match C with blah, 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 and with 3 holes here, okay? A hole for this one, a hole here, etc. Okay. And okay, I have exactly the same situation. I can show the proof, okay, as before. We see you see the fun followed by the match, etc. Let us undo that. I will show you something else. Yes, because you see that now I have more freedom than before. Before, I could use only intro and destruct, so I could do some very basic steps. But now, as I have the power of programming with holes, so the program, the piece of program I provide here now is okay. Okay, so I restart from the very beginning here. You see, okay. Yes, because I put okay. Sorry, I have been okay. I was too fast. Sorry. Here I make an undo 2 in order to restart from the beginning. So what I was saying is that instead of saying intro then district, I can perform these 2 steps at once and saying, okay, I want to say that my program is a fun followed by a match. So this is my refine is doing that. It corresponds to the proof I showed at this stage here. So I can, instead of saying 2 refines, I can write 1 refine. Okay, and it works. Let us go back again. I can make 1 refine and say, okay, for instance, for this one, I already know that I want to put a red. So this, okay. So you can see the freedom that I have. I can write actually inside a refine any shape of a program, well typed, of course. And all this has to be well typed, okay? Any shape with holes and using the constructs, you know, so that is basically fun and match, and maybe others, for instance, function application. Here I don't have any function application, but I could. Here I could, for instance, say next color of green. I could use a function that I already used. Okay, so I can write any piece of program, and this is what is funny. I have an interactive way of programming where some parts I already know what I want, and other parts, okay, I am a bit hesitating, so I leave a hole. Okay, so now I have 2 holes, so I will have 2 sub-goals. Let us try. Yes, 2 sub-goals. For the first one, I say, okay, so I could say it is exactly orange, but as I said before, refine works anyway. So refine orange. Okay. So if you need to remember only one tactic, it is refine. Refine in Coq is it. So I don't know why in the manual they have 900 pages. I think 1 page should be enough. Okay. And refine green. Okay, that's all. So we can print it. Okay, as usual, it is exactly the program, etc. I think maybe it's time for a pause. No question? No question, I mean, is outside of this room? Okay. So either it means that people, it means that it is very clear, or that everybody's sleeping. Can you see how many students are following today? Because I remember that yesterday maybe something like 80 people were following. So maybe today not too many. Do you know how many students follow the lecture outside of Zoom? Because I use Zoom and then you have another.
Today students number online is less than yesterday.
Yes.
Okay.
Okay, it's still enough. So maybe, okay, maybe I will wait still 1 minute for Professor Deng. Yes, he just received a phone call, so maybe he's done. So you can go on and okay. Anyway, he knows already a lot, so it will be easy for him to recover correspondence. Okay, so let us resume. Summarize. So we have seen that functions can be described at once as usual. Theorems usually are developed interactively. Okay, we have seen that functions can be developed interactively. So could we also develop theorems at once? Okay, and okay, so I will make more precise what we have seen. So what is behind this is something which is very important in all proof assistants like Coq, which are based on a functional programming language. This is called the Curry-Howard correspondence. So in the name of two famous logicians who remarked that maybe something like in the 50s, I think, so 50s, 60s. So okay, some decades ago. So the idea is the following. So if P is a proof of formula F, okay. So when we talk about logic, we have basically formula to prove, and we at the end when we succeed, we do have a proof of the formula. Okay, so we write this P is a proof of F like this, P colon F. Okay, so you recognize the notation. Okay, so the notation is exactly the same that we used in programming, which and the notation meant this is an object, something of type F. It could be a data or it could be a function. Okay, this column means has the type. Sorry, this one is the type of this one. Okay.
So the meaning of the Curie-Howard correspondence, it states that actually the proof P can be seen as a data or a piece of data or a piece of functional program of type F. So the correspondence is that a type is a formula and the program is a proof. This is a thing to remember. So I will say from time to time I will say program, I will say function, but always it means functional program. Okay, it is not a program. It is not a C program. And function. It is more than the notion of functions that you have in set theory. Similar, but we really see that as a program which computes something, a function which computes. Okay. There is a difference because in set theory, for instance, you have the function which takes, okay, for instance, a function which takes, okay, saying a list and returns the same list but in ascending order. Okay, so it is a function for sorting. Okay, so from the point of view of set theory, all sorting functions are the same. You take the list 1, 3, 2, and you return the list 1, 2, 3, whatever. Okay, but for us computer scientists, programmers, it is important to say that some programs are very efficient and some other programs are not that efficient. So they compute in a different way. So the notion of functions that we have in programming is more accurate than the notion of functions that we have in set theory. So just to say that when I say function, I mean a program, a functional program. Okay. So in this correspondence, so the types, okay, so correspond to formula. So we have two types of types. You have basic data. I mean, in programming, for types, you have basic data. For instance, we have TL color. Maybe we could say also NAT in some sense. Okay. And we have functional types. For instance, so the types that we root with arrows. As you remember, for instance, the type of next color is TL color, arrow, TL color. Okay. So similarly, we have seen that the statements of theorems that we have, they were built with not basic data, but basic equalities, I would say. And we also had implications written with the arrow. And we also had universal quantification. Let us take these things one by one. So basic equalities, I will talk later. But the important thing here is the first thing to start with is arrow. Okay, so we have arrows which are used for functional types, and we have also arrows used here. Okay, and the reason is why we use the same sign, the same arrow. This is because we really see a proof of P implies Q as a function, a program, which builds a proof of Q from any proof of P given in input. This is a very meaning. This is a very, okay, the important thing behind the Curie-Howard correspondence. And the meaning of the arrow. The proof, okay. So implication is just a program which takes an input and provides an output. Okay. So nothing to do with something like not P or Q. This is completely different. And by the way, which is not sometimes misleading. So here we have something which is that, okay, it corresponds to, I would say, to everyday natural reasoning. By the way, this is what in proof theory reduction. Okay. So when you want to prove P implies Q, what do you say? You say, okay, let us assume P, And using this assumption, I will prove Q. Okay, so P, each time I have a proof of P, I will provide a proof of Q. So this is something, okay, I talk more than usual by adding the proof everywhere, but basically I say from P, I am able to have Q. Okay, this is the very notion of implication. And just adding more accurately that, okay, from any proof of P, I will have a proof of Q. Okay, so I have something which is closer to computation. Okay. So now I said that I have data. Okay. So we will see later that we can really have tree-like structures for proofs. Okay. So we have tree-like structures for data in computing, binary trees, AST. So okay, you know that, or we will go back to that later. And for proofs, that's the same. We will see that we have a real notion of proof tree, and equalities are kind of degenerated proof trees in some sense. Okay, so I don't insist too much on equalities now. Just remember that proofs in general could be trees, proof trees. Okay, and now go to the third thing. So I have basic things, arrows, simple arrows, application. And I also said I have universal quantification. So this is new from the point of view of typing. But anyway, if you just look at the intuitive meaning of a universal quantification, what do you have? What is the proof of for all P? So for all X, P of X. What is a proof of that? This is just a function which takes any X and returns a proof of P of X. This is just that. So you see that actually, a proof of that is a function, like in the case of P implies Q. But here it is a little bit unusual. But anyway, it is also a function. Okay. No, sorry. What did I do? I mistyped something. You type no. Okay. Okay. So because I want just to point to have my my blue region progressing. Okay. So I will add a little words on universal quantification, because you could see that when you write an interesting theorem, and actually all theorems we have stated before are basically universally quantified formula, which could say, for instance, for all C, which is a color, then blah, blah, blah of C. Okay, something like this. So basically, any theorem, any interesting theorem has a quantification at the beginning. Okay. So now, if I want to interpret this as a type, I have to go to something which is not in usually programming languages, including the good functional programming languages like we like OCaml. So this new feature is called dependent types. So I put the word now. So we will go back to this very soon. Just remember that we have something new, which is called a dependent type. Okay. The point is that dependent types are a little bit more complicated than usual types. So it is not by chance that we don't have this for usual programming languages. It makes, okay, you have to take some care with that. So let us just remember that there is something to be seen later. But for now, we can go to something which remains simple. So I want you to understand something very simple now here. So this is the following. Sorry. want to have all the text on the lines. So, okay. So this is the following. So consider a theorem, okay, which has this shape. Okay, so just a formula which is theorem T, which says that for all x in some type, then blah 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 of x. Okay. Some expression E, which has the type some type, the type which is accepted by my theorem. Okay. You could say, okay, for instance, imagine a theorem T which is for any color, blah, blah, blah of this color. Okay, so I could say, okay, but what happens when the color is green, for instance, or when the color is a next color of red or whatever. Okay, some color, something which could be complicated, but of type color. Okay, so you could say, okay, but my theorem applies to any x of a type, say color. So it could, I should be able to use this theorem for this specific color. So when we talk about proof theory or natural deduction, we call this quantification elimination. It's a big word, but this is a big word for something which is very simple. If you consider the point of view of functional programming, we just say that actually T, my theorem T here, is applied to this specific expression E. Okay, so I just say that TE makes sense. Why? Because, as I said before, T is a function. T is a function which takes x as input and returns something. You just have to remember that T is a function which takes x as input. So if it takes x as input, I can take E as an actual parameter. Okay, so this is so TE makes sense. And now what will be the result? Maybe the result will be complicated because it is a proof, but anyway, it is a proof of what? It is a proof of blah, 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 not of anything, but blah, blah, blah of E. This time you see that the result has a type blah, blah, blah of E, of the specific E I had. So let us see an example, it will be maybe more clear. So I consider the previous theorem stated by for all C, next call of next call of next call C is equal to C. We have seen that before. Okay, so let us prove this theorem, and I will be very fast. Okay, if you want to be slower, you go back to the previous development. So I say destruct C, reason by case on C. And then I know that by computation, okay, remember that reflexivity can embed computation. Okay, we will, okay. Actually, there is something to be explained here, but it does not matter at the moment. Whatever is the proof, it works. And I have my theorem. So instead of T, it is called now with this long word. Okay, so now, I could, for instance, say, okay, I want to take an example of next ID, and I take for C, I take next call green. Okay, you see that I put C for C, I take next call green, and I expect that it should be next. Okay, this is the same expression. So let us state this theorem. Okay, and I want to prove it by using my previous lemma without computing, for instance. Okay, so if we want to see what happens, I need to show more. Come, please. Please. Oh. Pénible. Ah. Okay. Okay, so this is okay. Okay, so okay, the statement is a bit long. Next all of next all of next all. Sorry. Okay, so what I want to do is to use my previous theorem, and in order to see how I could use it, I could, for instance, try to apply it as a function. So I see that this theorem is like a function. It is a function actually, which could be applied to any color. So, for instance, let us try what happens if I apply this function to green, this theorem to green. So I check it, okay? And what I get here is next color. Okay, see what happened is what I have to look at is here. Next color of green is equal to green. It's not the same as here because I should have on the right next color of green. Actually, I have 4 next color. I have only 3 here. Okay, so it is not the right actual parameter to be provided. Okay, but now I, of course, try with this parameter. Okay, so now I apply my theorem to next color of green. Okay, and what do I discover here? Next color of green. Of green, it is exactly the statement I have to prove. Okay, so I check that it is right, and now I could say, okay, refine or exact. Okay, so I use this formula, this expression, not formula, this expression, and say, okay, this is my proof. Okay, and finished. No more gold. I'm finished. Now, okay, I have seen an example with a specific constant color, which is next color of green. We have also seen what happens with the constant green, by the way. Now I will do something else. I will prove the equality in the opposite way, okay, with C is equal to that. Okay, let us try to prove this one. Again, by using the previous theorem. I could prove it directly, but it is not my point now. I want to reuse my previous theorem to prove this one. Okay, which is a symmetrical formula. Okay, so let us again introduce some color. I call it C1. This is my choice today. Okay, so I have some color C1. And I have this statement. I want to prove this thing. What could I do? I have a theorem that says that this thing is equal to C1. Actually, the theorem says more. It is for any C, but I can apply my previous theorem using C1 as an argument. Okay, so okay, so show proof, no point. Okay, so let us see what happens if I apply the previous theorem to C1. Okay, I see that I get an equality. Okay. Oh, sorry, I get this equality. It is not the equality I want to prove, but it is an equality which is interesting, because now, if I see this one, I say, oh, I have this conclusion. I know when I have an equality, I can use it using which tactic? It is an equality. How to use an equality? Using rewrite. Okay. So I can rewrite this thing. Okay. So by rewriting, then this expression here will be replaced by C1. Okay, rewrite the function applied to C1. I get C1 is equal to C1. So it is finished by reflexivity. Yet another application, still more interesting. I will prove that next color is injective. Just by reuse the previous things. So, okay. So what I wanted to, okay, I add something. Usually, okay, actually, what I used yesterday, I think at some place without saying precisely what happened. Usually, okay, sorry, I go back to this place here. Okay. So usually you say, okay, I have a theorem which says that I can rewrite this expression into another one. So the usual tactic to be used is just rewrite next ID without argument. it works as well. But actually, it's cheating. It's much more convenient. We all do that. Not a problem. But I say, when I say it's cheating, I say that actually what Koch really performs is the next one. It is actually actually what happens is that in this situation, Koch says, okay, actually, next ID is not an equality like this. It is a universally quantified equality. And I will try to find, because Koch is somewhat, I wouldn't say clever, but he is able to do a number of digesting computation. Okay, Koch will try to find something which looks like the previous theorem with specific arguments, and we will see that sometimes it can make the wrong choice. But in that case, there is no choice because he has to find something which looks like like this. Okay, so there is only one possibility. Okay, and therefore we guess. Okay, the only possibility is to apply the theorem to C1. It does not tell you that. It just say okay. And now if I try the rewrite, Koch will complain, but he says, "Oh, I found nothing which looks like this." Okay, even if I repeat this one, I think I rewrite once, another time. Okay, Koch says something else. I am unable to find something which has this shape in the goal. Okay, so here you say how Koch proceeds. Koch proceeds by performing some guess and then finding the right argument to be provided. Okay, so I leave the explicit tactic like this. This is the real thing, okay, which is performed. Okay, and the explanation is in the comment. Now, let us go to the injectivity of next call. So what is an injective function? So it's a little bit of math. I hope we are not... okay, anyway, it is this statement, which says that the following, that if I am given two colors, C1 and C2, okay, I don't say anything about the colors at the moment. And now I put a constraint on these colors. I say that the next color of C1 is equal to the next color of C2. Okay, then I can conclude that C1 is equal to C2. Okay, this is what we call injectivity of a function. The function next call is injective exactly in this situation. When applying something to two arguments is possible only if these two arguments were equal from the beginning. So let us proceed as usual. So we introduce C1, we introduce C2, and we introduce an equality. I call it E. E is this equality. So you can see my new pocket. Okay, I have C1 and C2 TL colors, and E, which claims that I have a proof of this equality. Okay, somebody provides me an input, which is a proof of this equality. Okay, so now I can, okay, I would like to use the previous theorem, the theorem which says that C1 is equal to next call of C1. Okay. So I rewrite. And Koch did not choose C1, he chose C2. Okay, why not? It is still okay. So Koch, you saw that Koch actually has two choices. He could apply the previous theorem either on C2 or on C1. Okay, any color could be rewritten to 3 times next color of it. So okay, so Koch makes a choice here. Okay. Okay, now I would like to rewrite the C1. So okay, I hope that Koch will choose C1 this time. Bad. choose C2 again. I have to prove that C1 is equal to next call of next node of next call of next node six times. Okay, that's I did not progress here. So you see that sometimes just using a theorem using rewrite is not enough. I would like to rewrite not anywhere in my formula here. I would like to rewrite at this point. How do I choose this point? There I have to remember that performing a proof, making a proof is using functional programming. And I just have to say, actually, I can control the way Coq uses this theorem, the theorem, I mean, EID, blah, 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 by saying, okay, I want to use it on C1 and on C2, and not two times on C2. So let us start from the beginning on a clean state. Okay, so this time I say it is C1. I want to rewrite C1 in using the previous theorem. I am happy. This is the left-hand side. I have the control. And now let us rewrite C2. Good. I have next call of next call of next call of next call of C1 is equal to 3 times of C2. Okay. Now I can use my equality here. I can use and say, okay, this next call of C1 is equal to this next call of C2. I have next call of C1 here. Interesting. Let us rewrite it. Okay, rewrite the equality E. So this is a basic equality, nothing to be applied here. It is okay. Okay, no quantification. I mean, okay, so rewrite, a basic rewrite. So I have next colon of C2 is equal to the same thing. Reflexivity, I am done. Okay. So, okay, so this is I just reused what we learned before. We learned nothing new. Okay. We just used. Okay, so rewrite. What we use actually, what you had to understand is that a theorem, a universally quantified theorem, is can be a and this allows you to say, okay, I use the theorem for this or for that. Okay, and this is just a little piece of functional programming. Okay, so what I don't show you here, I will not. I won't show you things like compute this thing. I could try to compute them or make or print this theorem, because these are theorem on equalities. And actually, equalities are okay. Look a bit where the thing which is easy to understand intuitively, but in the detail it is a little bit too much complicated. But anyway, I don't know. I don't need to have to go into the details. What I only need to understand is that these theorems are functions. And by the way, here I get a new function. I get a function of two colors and an equality. So this is a function with 3 arguments, and this one. Next code is injective. It is a function, but if we read this with the eyes of a functional programmer, okay, we see a function with 3 arguments, this one, C1, C2, and a proof of equality. Okay. In terms of typing, again, it is something which is related to dependent types. Okay, and this is my next topic. Okay, so maybe I change a little bit. I don't know. I will save this one. Let us see now the next amazing thing. So usually when I teach Coq in France, my students have a little bit more time. So here okay, the lecture has to be given within a short amount of time. So you have to learn many things within only 1 or 2 days.
Or you can do some exercises.
Yes. Okay, so what I ask you, you mean right now? No, no.
That depends.
Well, I think I can proceed because okay, so the difficult part with difficult I would mean the new amazing thing will be presented right now, and then when you do the exercises, what is important is not to just to type the tactics as fast as possible. It is to remember what I told you and to interpret what happens on your screen using okay, all this scene, refine, functional program, and so on. Okay, so I will show you maybe the last amazing thing which can be shown on very basic things, always on the same example. Okay, will be large enough. So I will introduce you on these famous dependent types. And what you will get is that you will understand the exact meaning of forward in terms of types. I promised you to that there is some relation, and okay, this is okay. So just repeating what I said before, we develop a functional program, and we say that developing a type functional program and building a proof, basically these are the same activities. Okay, correspondence of Curie-Howard with a hyphen here is better. Okay, and this is especially interesting when we consider dependent types. Actually, it is also very interesting when we consider recursive programming. So, well, okay, maybe we will not see that today, but basically, when you go to with recursivity, it just means that reasoning by induction is actually performing recursive computations. It is okay. This is the last thing, the last part of the Curie-Howard correspondence. Okay, but in order to understand that, we first have to understand dependent types. So this is oops, sorry. Yes. Okay. So this is okay. I have to recover my large window. Okay. Maybe. Okay. So again, the same example. Nothing new here. Okay. Next color, always the same definition. So nothing new. So remember, we can define it interactively. Okay, so it is an opportunity to, okay. It is enough. Okay, so here I develop it interactively as before. So proof, exact orange. Second case, exact red, exact green. This is what we have seen before. It is just a reminder. We can also, okay, write. Okay, here it is another reminder, but directly things that I can write a refine with only two holes. Okay, so this function is defined using refine with two holes. Okay, I say orange, green. Okay, just a reminder of the first part. Okay. Yes, now I will present you another tactics that you may know, which is called apply. Okay, but it is just a special case of refine. Okay, so in order to show you this tactic, okay, this just some easy stuff before the dependent types. Okay, so apply, it is very common. Okay, apply is very common. So okay, let us consider a new function, another function without special meaning. I call it call NC, just for calling a new color with the same type. And this function, okay, the definition, the intended definition is here that I, instead of saying just a simple color, I use the previous function here. Okay, so nothing special here. But I want to say how it, what is in interactive mode, the corresponding thing in interactive mode. So, okay, so I perform my intro C, my destruct by case on C, show proof, okay, as usual. So the first is orange, okay, orange. So I just, sorry, orange. So I just say exact orange, okay. And okay, this is now here. I want a TL color and want this TL color on the right here to be computed using the next color function. Okay, so in order to say that I will apply next color. Okay, well, I say apply next color. I apply this function. This is just what means the name apply. Okay, so I apply a function. If I show my current code here, you see that. Okay, that's exactly what you expect. I have orange, which has been completed here, and on the for orange, I have next call of something to be completed, and I have the last goal to complete as well, the last case. So I said for this one, I want to say red, and then okay, here this is another one. Here I said instead of saying okay, this is not the same as this one. This one will be completed by next call of something. So just to show you that the apply is just a special case of refine. And you see that if I say refine next call of something, next call of a whole, okay, it is just say okay, the result is application of the next call to some. Okay, so this is refine that applied to that. It is like applied. So this is, you can see that as a shorthand of this special use of refine. Okay, so but once again, it is enough to just to learn refine, and you can do everything. And so I say green, for instance. Okay. So okay, so this one is okay. It is what the expected as far as you expect. Of course, this one with the next call. It is not the NC here. What do I show here? Using refine for developing code in an incremental manner. Yes, yet another example. Ah yes, no, nothing new. Oh yes, I say that I want to make a function, then make a pattern matching with two cases which are filled, and the one in the middle which are so okay, just nothing new, right? Just a variation on what you already know. Okay, refine with holes in another place. So here I put my next call. Okay, and I say refine. So here I only use refine. Okay, so basically nothing. Okay, now let us go to
I have a question here.
yes.
So what are the occasions?
Two.
The occasions
yes.
where you use this kind of interactive way of defining functions? Because it looks like developing proofs, right? But
yes.
You are actually defining a function, and then I mean, maybe for this simple example, we
yes.
already know how to define a function, even though you define it in a way as a proof.
Okay.
But are there more interesting occasions where you use this kind of interactive way of defining functions? Actually, we don't need it.
I agree. I completely agree. So personally, I very often use this refine mode for developing functions when I define functions on complicated types. When the types are, I mean, simple in the sense of simple theory of types. So it means made of arrows and basic types. Okay. Basically, you write as usual at once your program. But when you program with dependent types, it is more complicated because you have to plug things in a clever way, and it is almost, in general, it is impossible to guess at once the right piece of code. So developing a program with dependent types, I will go to this very soon, then use the interactive mode. Of course, in active mode, you could say intro and something, but it is more intuitive to say, here I want a function, here I want a pattern matching, there I want an application. But okay, as the types are more complicated, it's better to, the point is that you want to use the step-by-step refine when you want to okay, in French we say metro point. In French it is not debug, but I mean you want to design step by step your program by saying, okay, this part I know this type is okay, it will be this part, but I really don't know because it depends on what I have written below before or after. I don't know. And, okay, so when I have complicated situations with the dependent types, the refine is really useful.
Do you have an example?
The Braga method,
Yeah.
we use, you have to use the refine.
Okay.
Okay. So at the moment, just to, yes, I agree, just to saying, okay, we have the choice, but not such point, okay, not this interesting, but okay. It is just conceptually, it is the same actually, the same activity. Okay, so, alors, this one, I hope there is nothing wrong for this one. Okay, so maybe this one can be seen as a first example of a program with dependent types. Actually, if you print it, it is not that complicated but for okay, for bad reasons. So okay, sorry. What happened? Yes, I'm here. So okay, so you see, okay, if you see this as a theorem, okay, usually please just use intros, struct, it works. Okay, no problem. But now I want to present to give you the intuition of what happens on the programming point of view. So I really want to see that as a real functions. Okay, so why is it a dependent? What is a dependent type? So the dependent type is exactly here. What does it mean? It means that I have a function which takes an input C, okay, which is a basic type, nothing new here. But you see that the type of the result here, the type of the result depends on C. It is not the, but because you cannot confuse next column, next column, this column of green is equal to green. It is one type, and next column, next column, next column of red is equal to red. It is another type. It is not the same. Okay, so here I have actually three possible different types. Each of these types depends on C. I say C because C has three possible values. Okay, so this is why we call it a dependent type. And okay, okay. So we will not see all the difficulties right now, but we will just see that we are able to. I will just go a little bit further than before. Before I just said, okay, I don't want to show the code, but even if I don't know the code, I am able to see this as a function. I can apply this function. Okay, we have seen that before. We apply this function, and we said, okay, my theorem, I will apply it to C1 or to C2, and it makes sense. Okay, so, but now we will do more. We'll look a little bit inside the code, a little bit. Okay. Okay, proof. And I could say that, okay, as a function, it is, okay, yes, it is a fun of C, fun of the input C. Okay. And, Okay, refine, fancy. And we see that the type of the result here is something which depends on C. Okay, now we read that not on as a formula, we see that as a piece of data whose type depends on C. Okay. And okay, so I don't want to know what is this exactly what is an equality, but the only thing I need to know now is that okay, I need to reason by case on C. So I could say destruct, or I could say refine match. Okay, this is exactly the same. Okay, destruct and match. Okay, the difference is that in the match, I explicitly write the constructors. Okay, destruct, I don't need to write the constructors, but I need to respect the order. Okay, refine. Okay, and now I get the 3 proof of equalities, specific for green, specific for orange, and specific for red. Okay, I don't want to, at this stage, to look into what is an equality. I just know that reflexivity works. Actually, yes. One way of saying is to say, okay, there is this proof of reflexivity is called ref-equal, but actually ref-equal has some hidden parameters here. So there is a little bit of magic if you want. So okay, it works. I show you that it works. But okay, don't worry at the moment at the contents of reflexivity. Okay, we will show that later. No need to go to this detail. Now we will show you dependent types on something which is different and quite funny. So let us consider something else. So we have seen that, okay, remember this function, sorry, this one, next call, it takes a TL color data, TL color. I could return a NAT, and I'd say I returns 2, 3, 4, for instance, okay? Easy, this is usual. Now go to here, sorry, yeah. And instead of returning a data, I return a type, something which is completely new, which doesn't make sense in OCaml, for instance. Okay, so here I will make which return a type. Okay. I am able to write this because okay, it is possible. Set is visible in some sense. Okay, so let me write this function wow, which takes a color, so it has no special meaning. But okay, I just provide a type in each case. For instance, for green, I say, oh yes, my set is NAT. Okay, for orange, my set is TL color, and for red, okay, it is a function, a type of function. So TL, an arrow like this is also in set. Okay, it is a type. So all sets we see at the moment are of type set. Okay, so it works. Okay, so instead of returning a value, usual value in a data type, I return a type. Okay, and now I will use it. I will use it to write a function of C, my color, whose result depends on C. So once again, I'm playing with dependent types. But before I was saying that I had a formula, okay, it was not a data type, it was an equality, something, okay, so I forgot about equality. Now I have things for programmers. NAT is for programmers, colors is for programmers. Okay, functions, this is stuff for programmers as well. Okay, so now I will write a function of C whose result depends on C. So this is again a dependent type. Really, we see the dependent type. Okay. If I want to have a result that depends on C, how do I write this result? Okay, so I could not write, for instance, TL color arrow some type. Why? Because this some type depends on the output. Okay, so I need to name the input. I need to name the input. So in order to, what I do, so instead of saying arrow here, like here, or like before, I name the input. I say that the input is called C, is named C, and the result is wow of C. Okay. So it is again a function with an input, and the type of the result depends on C. So I cannot use arrow because the arrow I don't know how to refer to this, to the name of the input in the type of the result. But now, if I use this syntax, I gave a name to the input using the for all. So I say that for all C, for all, okay. Here I said that for all TL color, I provide a set. Now I said that for all TL color named C, I return this type where C is used. And now I can work, I can provide my code. So in order to satisfy Professor Dong, I don't need to go into interactive mode. I just write functional program like usual. So from C, okay, because okay, I take my function, so it is a function of C, okay, and okay, and actually, okay, this is okay. This is written, okay. At the moment, I can forget about this one, and okay, Coq will guess it. Okay, let us write it as close as possible as a program, functional program. I take C, and for green, I have to return a NAT. Okay, so I return a NAT, for instance, 2. For orange, I have to return a TL color. It is written here. Okay, so TL color, let us say green. And for red, sorry, for red here, I have to return a function. Okay, so a function of some color, some new color, some other color, and which will return a NAT. Okay, so I return, I called it C. Maybe it was a little bit misleading because I already have C here. It works, but I have a scoping mechanism. This C hides the other one. Okay, so it works, but maybe in order not to confuse them, maybe I will put a prime here. So, okay, you see maybe more clear, more clearly. Sorry. Okay, sorry, I put this on the top. Okay, I want to press here and want to remove this space here. Okay, okay, so you see, thing which has the type, which is which has been announced here in the type of okay, the type of the result. Okay. Now, actually, if I print it, Coq will say, okay, but okay, it works. It works perfectly well. But I checked that actually 2 has the expected type NAT here. Green has expected type TL color, and so on. I will really check it, and Coq actually remembers what was expected by saying return. Okay, this wow of C. And there is a subtle point here. There is a subtle point, which is that the type of 2 is NAT, you know. The type of green is TL color, you know. But it is not only NAT, it is also wow of green. So what happened here is something which is a little bit subtle, not that surprising, but important to catch. The point is that at type checking time, during type checking, Coq checks, computes this thing. It computes wow of C. It computes, for instance, wow of green. it says that, okay, wow of green reduced to nat. So we have a computation of wow, and okay, we see that wow of green is nat, and 2 has the type nat. So 2 has the type nat, and nat is also wow of green by computation. This is what is important. By computation, by reduction, I know that this is well typed. So this is a subtle term. Okay, see, if you don't catch it right now, you can think about that later. But the point is that here we touch a very subtle point, an important point of type theory, which is called the conversion rule, which says that if something has a type, say A, and by computation A is equal to B, then the thing I said, which has the type A, has also the type B. I mean, A and B have to be the same by computation. So using this computation mechanism inside the types, we have something very powerful. We could not write that. This function could not be written in a system which does not have this rule about this conversion rule of type system. So the typing system. This is funny because this is a very small rule in the big pages of the system, but this is the most important one. It is a very simple rule, basically, and nothing very surprising. And note that I insist on one point. It is the things have to be equal by computation. It is not a proven equality. Okay, if I have a theorem, completed theorem saying that, oh yes, blah 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 of green happens to be equal to nat. Okay, no, that doesn't work. This is not a theorem which is proved. It is not an equality. It is a computation. This is a very important point. So these computations have a very special status because they allow a type checking time of check that everything is well. Why does it not work with an arbitrary equality? This is because if you have an arbitrary equality, then you would need something like you have decidability problem, actually. So at the very beginning, in the Martin-Löf type theory, Martin-Löf wanted to add a rule saying that if things are equal, then blah, blah, blah. And as soon as he did that, Girard came to him and said, okay, your system is inconsistent. I think it's inconsistent. Yes, it's inconsistent. I think it's inconsistent, or at least anyway, it's wrong. Anyway, it's wrong. So it has been removed very soon. So it comes back to the very beginning of type theory, the 17th, basically. Okay. So
just remark what you said. It reminds me of something. I once had a problem with similar things. Saying, suppose I define a vector.
Yes.
A vector of nat, right?
Mm-hmm.
Dimension 1 plus 1. Another thing, I have a vector of dimension 2. Mm-hmm. I don't know that this two things are the same because even though we know that 1 plus 1 is equal to 2, but how do I not know that say automatically the vector of 1 plus 1? Okay, so in the case of 1 plus 1, it should work. Now, no, I will give an example which doesn't work. Yeah. If you say 0 plus n, you need variables. If you say 0 plus n, it will accept it to say, okay, 0 plus n is equal by reduction to n, because plus is written in this way. But if you say n plus 0, you are dead, because n plus 0 does not reduce to n. So it depends on the way. The example was expression, but I think they're just constant. I mean, if you something like n plus n and 2n. If you have only constant always reduce. They can reduce. But the problem is that when you write theorems, in general, you have variables. Yeah. And depending on the place of variables, things can reduce or not.
Remember yesterday, when I root 2 times n, it's reduced by CBN to n plus 0. So you have the start of a reduction. But if you write the other way, that is n times 2, no reduction is possible. So this is sensitive to the way you write your programs. And this is also a hot topic. For instance, Thierry Strub worked from 10 years ago on something called Koch modulo theory in order to add conversion rules to help you to typically this kind of situations.
In this kind of case, in order to make the proof work, so we have to explicitly define some kind of coercion rules.
So you are not free to do that for free like this. I mean, adding conversion rules because here you touch the kernel. Okay. So as a basic user like me, what you could do is to very carefully write your functions and have to know that in some, according to the way you write function, you can do things, and if you cannot reduce, then you can do. Typically, for the kind of point you think, I think probably you need to do some kind of advanced pattern matching. So we will see maybe next week. But yes, so what I could claim here is that we can already write a number of things that would be impossible in other kind of languages without these conversion rules. Then people would like to have more conversion rules, and then then here we can enter into the some tough things of dependent functional programming. So a number of things as possible, maybe not as much as we would like to have, but okay, it's already better than nothing. And in particular, this very feature allows you to provide something which is called proof by reflection, which is a very powerful mechanism for teaching Koch, in some sense, new decision procedures. Enriching Koch by decision procedures in specific theories can be done very efficiently thanks to this mechanism at the end. Okay, so this is already interesting, even if, for example, with vectors sometimes we have problems. I agree. Okay, so what? Okay, maybe we can go a little bit further. Okay, so we can check what is this one for all C. Okay, yes. I show you something. Actually, we use the arrow. Okay, usually arrow, it is the type of functions from A to B. It went?
Yeah.
Okay. It is the type of function of A to B. But actually, we could say, okay, what is such a function? It is a function that provides an answer of type B for all input of type A, if I pronounce it in this way. Okay, so actually you can really, instead of arrow, write this for A, B. Okay, I happen not to use this small a, this lowercase a. I don't use it here at this place. Here I use the C is used here, but here on the right of the comma, here it is not used, but I can write this way. Okay, so for instance, I say here a function from TL color for this type, which to NAT, I can write, okay, this is a function which takes any C of type TL color and returns a NAT. And if I try this, like this, okay, but Koch print it this way, in the good old way. Okay, so actually, I told you that we have no, I didn't tell you that, but actually we have only one mechanism. So I mean, the basic things of Koch are made of actually only prop set, okay, this kind of things, some basic things, and on top of that, only one connector, which is not arrow, but which is for all. So the for all is how to say, the arrow is a special case of for all. Okay, inside the system. Even if Coq is clever and print it this way with an arrow, but actually inside Coq it is a for all. Okay, so I did this one written in the in the direct way as a function. Okay, and of course, as usual, I can do the same using functional programming. Here you can, it is the beginning of the answer of your former question, which is, writing these functions is a little bit, you have to be more careful. You have to be sure that this one has a right tip, this one as well, and this one as well. It starts to be a little bit more complicated. You see that here I have not the same tip, and here I even have a function. So, okay, you see that, so in this case, it may be a good idea to write it in the interactive way. Okay, so I have the code on the top. Now here I state my type for say so okay, I want a function. Okay, now I want a case analysis. Okay, on C. Boom. 3 cases to consider. So you can see that, okay, here you can see the beginning of the function, must see return. So you see that Coq already, prepares the right program, even if here you were a little bit, okay, here you didn't put the return because I am lazy, okay? Okay, so now I have to provide what we call a member of this type, okay, an inhabitant of this type. Wow of green, oh, it's complicated. What could be that? Well, maybe I could look at the definition of wow, but you look, my screen is too small. My function wow is very far. I don't want to look at my function. Let us just compute. Okay, so let us compute. What should I provide? Sorry. Ah, it is a NAT. Okay, so now I know what I have to provide. Say 2. Same here. I had to provide, or I don't know. Let us compute. Ah, this is the color. Okay, let us say green. And last one, what it is? Ah, it is a red. Okay. Okay, I don't know. Ah, it is a function. So now a function. Okay. Now, if I want to say, like before, I will say a prime. It is clear. And again, it is a destruct C prime. Okay, refine C prime, and so on. Destruct again, color. And for the first color, I will provide 1. Why not? Here it's just usual. I could say, okay, I have a mixture of refine and destruct here. Okay, so this is okay, and finished. And you see, I can compute even the first one is the same function. Okay, so you see something strange. This function here has 1 argument. The same function has 1 argument, and that's all. Okay, 1 argument. I provide 2. 1 argument, I get green. 1 argument, but I get a function. So actually, I could apply this to 2 arguments. So again, it's something you cannot have in OCaml. In OCaml, you always have the same type as a result, and it would be either data or okay, something which has a partial application. And so, okay, but here everything is possible. I can prove that my 2 functions are equal. They were developed using different, in a different way. So if I didn't make any mistake, oh, it's a bit French, same. Okay. 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 So maybe I could try CBN, but I am lazy. I will just try reflexivity. Okay, so once again, what happens here? You see, I don't see the same text here and there. There may be two different things, I don't know. But what actually happened is that these two things, computation after reduction, reduce to the same thing. Once again, we see that we have this conversion rule. Okay, we already used that many times yesterday and today. Each time I use CBN in my proof, actually, without saying that, I was using the conventional rules, which says that when things reduced, when one type, reduced to something else, okay, so okay, then they have the same. The inhabitants are the same. Can be promoted. Where yeah, okay. Okay, see, just to say that, okay, see, we see the full code with the returns that, okay, so depending on if I am lazy or not, I could write the return clause. So actually, Coq printed a little bit complicated way because we see C as C0. What is the point to introduce a new name? Okay, so the reason is that in general, here, you don't have just a variable, you could have any complicated expression. I match a completed expression against the different patterns, green, orange, red, okay? But this completed expression has a type, and in order to say return something, I have to name the result of this complicated expression. Here it is not complicated, it is just a variable. But in general, it is okay. We'll say okay as something, just a name, and we say that the result depends on this whole expression, which is on this name. Okay. And the rest is okay, nothing new. So this is print wow. And the second one, maybe it should be the same. Well, I'm not sure. Not maybe okay, maybe something that is yes, I think here he said wow red. Not, I think not in the previous case. He could actually, so the code could be a little bit different. Let me see. I think here, yes. So you see, it is not exactly the same. Very close, sure, but not exactly the same. But anyway, they reduce at the end to the same thing. Some additional computation can be made on one or the other, and then they reduce to the same. Okay, but actually, here happens to how to say to remember. Okay, the two codes which are a little bit different. Okay. So what do I have here? Oh yeah, so this is the same as before. Just to say that okay, so my famous function here is written this way, but actually once again, this eqref here is a kind of what you see here is not exactly. I mean, the eqref here is not the eqref here because they don't have the same type. This one is a proof of blah 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 of green is equal to green, and here again. Okay. So what you see here is not actually hides a little bit of stuff because Coq choose to. Okay, for convenience, it's better to have to shorten what is printed, but actually maybe. Sorry. So now.
So what's eqref is that is not happy from
eqref?
Yeah.
No, it is a constructor of the inductive type equal. So it is okay. So, but it is not that complicated. The problem is that equality is something which is very general, which has to be defined for any type, etc., etc. So it has a number of parameters, which makes things at the end a little bit headache. Okay, it is not very complicated, but okay, so it is a bit annoying to displaying so that much. So if I print my, okay, so this is I kept it with a French word, but anyway, just yes, okay, you could see here that with the return type. Maybe I should go here. Yes. So you see that I have here. You see that actually the EQRF will have a type that depends on what I have. Okay, so actually, okay, so C0, this C0 will be how to say, will be equal to respectively green, orange, and red. So this referential actually is referential of type next to the linear of green is equal to green. I can show you. Yeah. Of type. So type like this. So, but I put a green. The green here again. So here I am more accurate by saying that. So you guess that in general you don't want to put all this information because it makes your screen full of many things. So programming with dependent types is we have to find the good trade-off, the good balance between things you would like to see to be sure that you are right, and things you don't want to see because you don't want to be disturbed by too many details. This is so this is why in general when you program it with dependent types and actually proving theorems is exactly like this. It is an interactive definition of a function. The only difference between theorems and this kind of thing, as the programming with dependent types, is that usually when you write a function, you want to compute with a function. So you want to reduce that. This is what you did before. What we did before, we were able to apply this function to something and see that actually, yes, it's reduced to something which is interesting. For theorems, in general, you don't want to compute. You want just to say that, okay, I can apply this theorem to this value in order to use it. You have seen rewrite theorem, blah, blah, applied to color thing, okay? I want to see that it could be applied and get the right thing that can be used for my rewriting. But that said, I am only interested in the type. It is a proof of this equality. So if I want to reduce, for instance, all my theorems until now are quantification, equality, maybe an implication in the middle. So basically, all my theorems are about proving an equality at the end. So if I perform the computations on such theorems, at the end, what I get is just ref equal. Okay. At the end, after computation. But I don't care about that. It is enough to say, okay, this is by using theorem T, theorem T1, blah, 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 combining all these theorems. So I make a big proof tree, okay, which says that I could perform the computation, but at the moment I don't make the computation. I keep my proof tree, which proves that at the end, A is equal to B. I have A is equal to B. I am happy. I rewrite. Okay, I know I have something which could, if I wanted, this could be reduced to ref equal, but I don't care so much in general. There is one situation when we want to really compute on proofs. This is when we develop programs using a structural decreasing, when the decreasing argument is a theorem.
Mhm.
in this realm. So okay. But okay, well, anyway, so if you forget a little bit about computation, you see that this is the same activity. So what I just said, it is about the difference between defined, okay, I finished my definition, and QED. When I say QED, Cook understand is that, okay, you have your function, you have your thing, but I don't care about computing, and anything which has been defined using QED, you cannot compute with it. And this can explain some strange some first sight strange behaviors of code. You say, oh, but I have my theorem, I want to compute with my theorem, but why do I keep this huge proof tree? Okay, this is but because usually your QED is enough. And it's kind of optimization because when Coq see a QED, maybe some things, okay, it makes an internal optimization in order not to keep too many things. So defined, it takes a little bit more memory, I think. But basically, but the basic mechanics is the same. And you always can finish a theorem by defined, and you get a function, which can be computed.
Yeah.
Okay, so I think that's enough for today. So I put this material on my web page. Okay, I will correct the mistakes, finish the translation of the French, and so once again there is some material I put in advance about using all these theoretical things on AST, okay. And so we will illustrate all this later. Having this in mind, we'll be able to do many interesting things on the semantics of programming languages first, and then, okay, so I think I will have time to explain advanced methods for developing recursive programs.
Okay.
Okay, I think we already have a good background. If you understand all this.
Yeah, for me, I understand. I don't know.
But okay.
For the audience, I don't know.
Yes, but okay, don't worry too much. Don't worry too much. First, I wrote a number of explanations, so you have the time to reread. You have the time to ask questions. Professor, I didn't understand this small paragraph. Could do. Okay, I can understand. I can answer. No problem. So it will help me to make my material more better. Okay, so don't hesitate. I prefer to have feedback from you. Yeah. And to improve my material for next time and for all others. Okay, so please give me feedback. If you don't understand, it doesn't matter. Okay, say me. Okay, this point. Okay, I would like to have more details. Okay, okay, tell me. And second, anyway, what will help you is as usual practice. So, but clever practice. I mean, not just fastly run at the rush at the end of the theorem. Right, things, okay, it means this, it means that, I understand, I don't understand, I have to look, I have to ask questions. Okay, and you progress this way with the examples.
Yeah.
Okay, so
okay.
See you tomorrow. Okay, yeah. If you have questions right now, no problem. Okay. So, okay.
有问题可以发邮件或发邮件给那个陈梦阳老师。那没有。
让我再看一下。
让我再看一下。Okay, for the lecture, that's all.
Okay. I remember you had two questions from.
Yes, sir.
I answered one of them, and there was a second question about laziness. I remember.
Yes.
Okay. Well, maybe how could you proceed? It could be possible to dispatch my answer to everybody, or
Yeah.
if it's possible, okay. And anyway, I can start with that.
You can leave a message from 不，是他的回答，你要到时候放到那个里面。
对，这就是老师的那个。
他的回答啊，你已经回答了。You already answered.
Yes.
Okay. So
Yeah,
you
yeah,
can, yeah, put a message on the chat room.
Usually a question means that something has to be
Yeah.
could benefit from additional explanation. So
Yeah.
okay, no problem.
Good. Okay. That's
Thank
okay.
you for attention.
Yeah. I can finish the morning session.
Okay.